All right, APCal class, we're continuing on with our notes for section 4.2, working on area and sums, and they call them Riemann sums. I haven't really used that term yet, but we'll see it more as we move through. Okay, so this is the last example that we had finished, and I just want to reiterate a couple of points in here. So we had used the midpoint rule to approximate the area under this curve 8 over x squared plus 1. And so that midpoint rule was telling us, when we draw these representative rectangles, which give us an estimate of the area under the curve, where do we want those rectangles to intersect the function, right? So with the midpoint rule, we want those rectangles to intersect the function right in the middle, and so that's what we were seeing, when we drew these in. We were intersecting those rectangles right in the middle of the rectangle. And so where does that appear in our work? These, f of 5 halves, f of 7 halves, and so on. The 5 halves, the 7 halves, the 9 halves, 11 halves. That is the x-coordinate of the input value that calculates the actual height of the rectangle, because that's the function value. Okay, and then also I want to reiterate here, the width of the rectangles is this formula b minus a over n is going to be a consistent formula that we use when we're looking at these types of problems. And so in this case, our interval from a to b was from 2 to 6. And so 6 minus 2, and there were 4 rectangles, so that was the number that was divided by 4. So 6 minus 2 over 4 turned out to be 1. So this 1 out here is representing the b minus a over n, and then we aren't using the summation, that sigma notation in here. We were just adding up the 4 pieces, but as we go into this next example, we will be using that sigma notation. So really what, we'd see, okay, it's the sum of each of these function values from 1 to 4, and that's really what we've done here. Or actually, technically, it would be from 2 to 6, but we'll get into some of the details there a little bit more as we move on. Okay, so, and I've actually worked this out to save time because this one, fairly complicated problem, but I want to explain it thoroughly, and we'll take a look at each piece of work here step by step. Okay, so it says, let's take a look at a problem that doesn't give us the number of subintervals. So in other words, what that means is n, and that's what it says here, n subintervals. We just leave n in there instead of knowing, like in this last example, we knew that n was 4. And so we just put that 4 in there, and then we were able to simplify and have a numerical value there. Okay, but this one's going to be a little different because although we do know our a and b, we know the endpoints of our interval. In this case, it's going to be from 0 to 2, so a0, b is 2. But this time, we don't know the number of subintervals, okay? And that being the case, there's going to be an upper and a lower sum. Because remember, right side rectangles and left side rectangles are going to give us different approximations. Now here, we don't know that. I just drew in 2 just because that was simple to draw in 2 rectangles here just to demonstrate the difference. But the lower, now this is an increasing function, right? It's this parabola from 0 to 2, it's increasing there. So the lower sum is going to be the left side rectangles, and I drew those ones in red because the left side of these rectangles, and actually this first one doesn't have any height at all, because if we start at 0, the height at 0 is 0, and so we just basically have no area there. But when we draw on the next rectangle, on the left side it intersects here at 1, and so that would be our rectangle there. So that's an underestimate clearly, because there's all this area above those that's not being accounted for. Now the upper rectangles in this case are going to be the right side rectangles. So if I were to connect these, the right side of these rectangles with the function, you can see that's an overestimate because we're adding in this area, which isn't actually part of what's under the curve. Same thing here, we're adding in all of this area. Okay, so again, we don't know that there's 2 rectangles. I just drew in 2 for demonstration. It's n, so it could be any number of rectangles, okay? So when we represent the width, it's going to be the b minus a over n. And now we do know b and a, so it's 2 minus 0. So that just simplifies to 2 over n. So, when we add up these areas of these rectangles, the width of all of them will be 2 over n, whatever n happens to be. Okay, so I started with the right side endpoint rectangles because the formula for that is actually a little bit simpler, because when we start, basically the idea is that every time we write one of these sigma notations, it's it's more proper, or it's more common to start with I equals 1 instead of I equals 0 down here. So we want to start with I equals 1, and that way the right side of the rectangle will always be your first function value. And so that's why this formula becomes just a little bit easier. I'm going to scroll down here and just kind of show you some of these. So we've been saying this, the width of each rectangle is always b minus a over n. Okay. Now, the length, they say length. I always say height because they're going up, but it means the same thing. So length there, I'm always using the word height when I say this. So height, height times width or length times width, whatever. But I like height because it's going upward. Of the right side endpoints. Okay, so so you do have to, so it's f of, and then if you don't start at 0, you'll have to put in a different number there. Like if it was from 2 to 6, like that previous example, you have to start at 2 because we have to move to the x coordinate, where we're starting. And then it's the width of the rectangle as you move through it times the counter. If it's the first one, then I is 1. If it's the second one, then I is 2, and so on. Okay. However, if you are starting on the left side, if you're using the left side endpoint rectangles, if we want to start with our summation at 1, we have to put this I minus 1, because if you look up here, on our left side rectangles, the first one has to be really like f of 0 right here. And so that's why this I minus 1 is part of that formula. Okay, on the right side ones, your first rectangle is, I equals 1, and that's where the right side of it hits. However, you have to go backwards 1 for this one, and that makes the formula slightly more complicated. Okay, so I just want to point that out. So I'm first going to go through, they want us to calculate the lower and the upper, and we said here that the right side rectangles are going to give us that upper sum, so I'm doing that one first, and that one's actually simpler. The right side rectangles are always a little simpler. But let's see if we can kind of work through this together. So you saw it was b minus a over n, that gave us 2 over n. Then on the right endpoint rectangle, so our height or length is going to be f of, remember the formula was a plus, and then it was I times b minus a over n, and our b minus a over n already here, our width was 2 over n. Okay, and so simplifying that, since we're starting at 0, it was a plus it, so 0 is first. That's just going to simplify to 2i over n. Okay, so if I multiply those, just 2i over n. Okay, and that's going to be my function, my height of each of the rectangles as I would go through. Okay, so height times width, that gives area, and then we're summing up all of the areas of all the rectangles in there. Okay, so that's kind of how we interpret this. It's the sum of the height times the width, and that's going to give us the area under the curve, okay, or approximated area. Okay, so now, because there is a specific function that goes with this, f of, right, and our function is x squared, so we put the 2i over n into that function, so it's 2i over n quantity squared, width stays the same, right? And I'm just going to simplify this. If I square this out, I would have 4i squared over n squared, so 4i squared over n squared times 2 over n is going to give me 8 over n cubed, and then I'll still have the I squared. Okay, hopefully that's making sense. We have a little algebra to simplify there, but this is 4 times 2, so that's 8, and then you've got n squared on the bottom times n here, that's n cubed. All right, now this is where we have to go and use some of those summation formulas from the beginning of these notes to continue on from here. Now, at this point, if there's a constant, that's going to be the same, like the stuff with the n in it, if we can factor out, and since there's only one term, we can factor out the 8 over n cubed, we'll just pull that out and deal with that at the end. Okay, what we're interested in are the terms that contain i's, because those are, that's what we're going to use for with our summation formulas, because this is, from I to our wherever we finish at n. Now the formula for I squared, the sum of something with I squared, I have it written down, but I just want to refer back to it where we did talk about it a little bit earlier. They were kind of at the beginning here. Some of our summation formulas right here, and we did one of them with some numbers here before, but the I squared formula, n times n plus 1 times 2n plus 1 over 6. Okay, and so we did that where we had some actual values to plug in there, calculated that out. But this is where it's a little more abstract because we don't actually have numbers. We're just leaving n in there. Okay, so that's where this comes from. So the I squared formula, n times n plus 1 times 2n plus 1 over 6. Okay, so now this summation symbol disappears because that's giving us the sum of the terms from 1 to n of, when we have I squared, okay? That's how that'll calculate that value. The 8 over n to the third is still outside of this. Now, as I would simplify this is going to, a little bit of algebra. I'll see if I can talk through this. Now, this 6 that's in the bottom, because there's just this one fraction here, I'm going to pull that out here, okay, and put it in the denominator and then simplify. That's why this became 4 over 3n cubed, okay, because that's 6, so it's 8/6, which is 4/3. Okay, and then here we're going to FOIL this out, and it'd be like 2n squared, and then outer would be n, inner would be 2n, so that's 3n, and then plus 1. And then if we distribute that n through there, 2n cubed plus 3n squared plus n. And then finally distribute the 4 over n cubed and simplify. So this would be 8 over 3. The n cubed on top cancels the n cubed on the bottom, so it's just 8/3. Similarly, just distributing, this 3 would cancel the 3 in the denominator, and then you've got n squared on top and n cubed on the bottom, which just leaves us with just n on the bottom. And then finally here we'd have 4/3. It would be 4n over 3n cubed, but then the n on top would cancel 1 on the bottom, leaving us n squared on the bottom. So this expression right here represents our upper sum, and that would be for whatever you want to use for the number of rectangles in there. So if I wanted to say, if we did 3 rectangles, I'd just put a 3 in there, for the ends. If I wanted 10 rectangles, I'd put a 10 in there, and then that would approximate your area. Now, hopefully you're getting the idea that if we break it up into more rectangles, making their width smaller and smaller all the time, that's going to fit this curve a lot better. That's kind of the idea here, and we're going to see how, when we move to this limit process, that's kind of what we're doing. So when we introduce this, same as like when we were trying to approximate the area of a circle, if we made more triangles in there, the geometric shapes more closely fit the curved shape of the circle, right? And so that's going to be the idea here. So the next step to this is going to be, well, let's find the limit as the number of rectangles n approaches infinity. Okay, so as we put a higher and higher number for n in here, we're going to actually approach the actual value of the area under the curve, and that's really the big idea of what an integral does for us. Okay, so I know a lot of this is tedious, but getting background on what we're really, how we're getting to this point. Okay, so that was the upper sum, and unfortunately that was the easier one. I'm going to talk it quickly through the lower sum, because that in this case is the left side rectangles, which has a slightly more complicated formula due to the fact that we have to have this I minus 1 so that we can start at 0, f of 0 for our first height, which in this case gives us 0 height for this first rectangle, but just to visualize that. Okay, so what we do here for the height, so it's f of a, which is, we're starting at 0, so we don't have to add anything there. 0 plus, and then in this case, I minus 1 times 2 over n, right? And that 2 over n again is our width, right? We saw that up here. 2 over n is our width. So this is height. I'm sorry. It's f of this, and our counter is going by our width every time. Okay, and then so that's our height, and I simplify this a little bit. That if I distribute 2 over n through this I squared minus 1, it would look like, this would be an expression. I guess I just put the 2 on the outside there, but n would be in the denominator. So it's f of 2 times I minus 1 over n, and then my width here, 2 over n. Okay, and now as I go through and try to simplify this a little bit, I'm going to FOIL this expression up here on top. So if I square the 2, that's 4, and then 4 times this 2, that's where I get this 8 right here. Okay, and then n squared on the bottom, that's what I'll have, times this n is going to be an n cubed. So that piece, I'm just kind of, this 2 over n, and then this 2 over n that gets squared, I'm still going to have this 8 over n cubed like I did before. But this piece here, this numerator, instead of just being I squared like it was here, because it has the I minus 1, it FOILs out to I squared minus 2I plus 1. Okay, so that actually means we're going to have 3 terms that we have to use the summation formula on. One that's I squared, and one that's just I to the first, and then one that's a constant. And again, just referring back to what we had here for these formulas, we have a formula for I squared, which we already used, one for I, and that was kind of the one I talked about here with Carl Friedrich Gauss, how he kind of came up with that one. And then if there's a constant, just the constant times the n. Okay. All right. Okay, so right here. Okay, so we have it. So this piece again, we're gonna factor that out. The 8 over n cubed is gonna come out in front of the entire expression, and then we're gonna do a separate sigma notation for each of the terms in there. And so I've set that up in that way, just like that. And then with that 2, I'm pulling that one out as well. The 2 can come out in front of that expression. You can always do that with any of your coefficients. Okay, and then we're going to use each of those summation formulas. And so this one was the same. It was n times n plus 1 times 2n plus 1 over 6. And then the minus 2 there. And then the I formula was just n times n plus 1 over 2. And then finally the constant formula is just the constant times n. And since the constant's 1 times n is just going to be n there. Okay. Now the simplifying here, this is obviously, that seems like the algebra gets real kind of tedious in here, and it's not like it's hard, but it's just keeping your work organized and getting through it. But anyhow, these 2's, I'm going to cancel those out. Okay, so I'm canceling out those 2's, and then I would be distributing. Okay, so there's an n that gets distributed through there, so it's n squared plus n, right? And then this minus sign, so I put those in parentheses. That minus sign needs to get distributed through there. Then I still have this plus n at the end. Okay. Now, if I were to combine my like terms, now what's going to be convenient here is if we get common denominators. So I'm doing that in the next step, and I kind of combine 2 steps in one just to save some room. But if you think about how this would look, okay, so it's going to be, when I distribute this minus, it's minus n squared, minus n, and then plus n at the end. So those n's are going to cancel. This plus n, and actually it's going to be a minus n in there, and then this plus n would cancel. And so I really just end up with minus n squared here. And so I'm going to get a common denominator. Since there's a 6 here, I'm going to say that this is minus 6n squared over 6, which is obviously the same as just minus n squared. But I'm going to do that because that allows us to, that we'd have just one common fraction here. What I want to do is I want that common fraction so I can just pull this 6 out of the denominator and put it down here, similar to what we did here, and it's going to give us, for that 4/3 n cubed on the bottom, like what we had before. And that helps us out for simplifying this a little bit more. So I've got that out there now, and then I'm going to combine the rest of these terms together. So 2n cubed, there's no other n cubed terms, and I have plus 3n squared, but I'm combining that with the minus 6. That actually ends up being negative 3n squared. And then I've got the plus n right there. Okay. And then distributing that through, it's basically the same as what I had here, except that changes to negative 3n squared because of this negative 6 when I combine it there. So basically it looks very similar, but this middle term is a minus 4 over n. And that makes sense. If we're minusing something, that's going to give us a lower approximation, a lower sum than what this one where we added all of the terms. So that's it. That's, how we calculate an upper and a lower sum. And really using left side and right side. And again, in this case, the right side endpoints gave us the upper sum because of the increasing. It was an increasing function. And the left side gave us the lower sum because it was an increasing function. But that's in general how you can write that. And so in the next couple examples, we're going to actually find the limit now, because now that we can do this, which is let's say the most tedious and difficult part is to get these expressions. Now we're going to say, okay, well, what's the limit as n approaches infinity? That's going to be the next step, okay? So as n approaches infinity, we're going to come up with a value. And if you think about that on these ones, if we were taking a limit of this expression, if n was approaching infinity, both of these would just come out to be 8/3, because each of these last two terms are going to become infinitely small and approach 0. So 8/3 would be the answer, which makes sense. They shouldn't be different values, right? They should be the same value as we have an infinite number of rectangles under there. Okay, so I'm going to stop here on this video, and then we're going to finish up the last couple examples on our last